Hi, everybody. So next Friday, we're having an exam, and I posted a study guide on the course website. And as usual, I'm telling you what you're supposed to know and what you're supposed to be able to do for the exam, which is next Friday. Since this is since this exam, we're giving it in a remote setting. The first page of the study guide has some instructions about how I'm planning, how I'm hoping to carry out that exam in this remote setting. So I don't want to take class time now to talk about the exam and about the technology and what you're supposed to do. I'll talk about that next time because I have to, I want you to go to the course website and read the study guide and read the procedure for taking the exam next week and what will be the deadlines and all of that other stuff. I don't want to take class time now. So I'm going to try to finish up the material for the exam today, but if I can't, I'm going to have to slop over into Monday's lecture. Okay, so we've been talking about at the last lecture, we were talking about what happens when an aldehyde or a ketone reacts with oxygen nucleophiles of an alcohol. And so that's going to fit in very nicely with our next little topic here, which we're going to talk now about some of the chemistry and some of the language and vocabulary and classification of the carbohydrates. Okay, so this is going to form the last topic for our exam of next week, which is the carbohydrates. Okay, so just bear with me for a second here. Here on my other computer, let me bring up some stuff. Okay, just bear with me. Okay, so what we're going to talk about now are the carbohydrates, which is the fancy word for the sugars. Okay, what is a carbohydrate? A carbohydrate is a polyhydroxy aldehyde or ketone or a compound in equilibrium with such. Okay, so a carbohydrate is a polyhydroxy aldehyde or ketone. And this fits in very nicely with what we've been talking about at the last lecture, because we were talking about what happens when an aldehyde or a ketone gets together with an alcohol. And polyhydroxy, well, hydroxy means an alcohol, it means the OH group. But in order to qualify as a carbohydrate, something has to be polyhydroxy. So let's just look at some examples of what is and what is not a carbohydrate. So something like this, oh, that's not a carbohydrate because it's not polyhydroxy. It's a ketone and it has an OH group in it, but it's not polyhydroxy. Something like this, that's not a carbohydrate either because it's polyhydroxy, but it's not a polyhydroxy aldehyde or ketone. Now, something like this, oh, that is a sugar. That is a carbohydrate. It's a polyhydroxy aldehyde or ketone. And so, first of all, what we want to talk about is a lot of the vocabulary associated with carbohydrates. We've already talked about the chemistry that carbohydrates engage in. That's going to be acetal and hemiacetal formation, and we'll return to that. But first, let's just talk about some of the vocabulary associated with carbohydrates. We have aldose. So we're going to erase all of this. I'm going to start again with the stuff that I would like for you to know about. I'm talking about carbohydrate vocabulary. Okay, we have, we can refer to some carbohydrates as an aldose. This is an polyhydroxy aldehyde. And some other kinds of carbohydrates are called ketoses. And this is a polyhydroxy ketone. Okay, so concrete examples of a polyhydroxy aldehyde or an aldose would be that. That's the carbohydrate called glyceraldehyde. That's a polyhydroxy aldehyde. That's an aldose. And a simple example of a ketose would be this dihydroxyacetone. That would be a ketose. It's a polyhydroxy ketone. Then we can also specify the number of carbons in the carbohydrate. And so we have a triose. This means there are 3 carbons in the carbohydrate. And a tetrose, 4 carbons in the carbohydrate. A pentose, 5 carbons in the carbohydrate. A hexose, 6 carbons in the carbohydrate, and so on and so forth. We can also talk about heptose and octose and all of that other stuff, but that's kind of a very rare kind of thing. So let's just stop here at the hexose. And then we can conflate the aldose and the aldose and this triose tetrose jazz to form yet another specification for a carbohydrate. And this guy, for example, so combine these two, and we get something like an aldotetrose, or a ketotetrose. This is telling me that it's a 4-carbon sugar that is a polyhydroxyaldehyde, or a 4-carbon sugar that's a polyhydroxy ketone. Aldotetrose, aldotriose, or ketotriose, etc. Okay. Okay, so this is just some of the fundamental specifications of a carbohydrate. Okay, so ready for a problem? Why don't you try it? Draw a ketopentose. Okay, so what does ketopentose mean? That means it's going to be a polyhydroxy ketone that has 5 carbons in it. There are many correct answers. Draw a ketopentose. Did you come up with one? Okay, so 5 carbons. 1, 2, 3, 4, 5. And now it's going to be a ketone, so I'm going to have to put a carbon-oxygen double bond somewhere, but I'm not going to put it here because that is going to make it an aldehyde. So I could put it there or there or there or there. Let your imagination run wild. So I'm going to put the ketone functionality there. So now I need to make it polyhydroxy. So all I need to do to finish this up is to draw in more than one OH group. So I could put one there, I could put one there, sure, why not? Okay, so that's a ketopentose. And I could just, go wild. I could just go wild and draw a lot of OH groups. So that would be an example of a ketopentose. Okay, normally, all of the carbons in a carbohydrate are oxygenated. All of the carbons in a carbohydrate are bonded to oxygen either by a double bond or by a single bond. So usually, or let's just say normally, all of the C's in a sugar, in a carbohydrate, are oxygenated. But some of the most important carbohydrates, in some of the most important carbohydrates, the carbon atom isn't oxygenated. These are called deoxy sugars. Deoxy sugars. Deoxy sugar has one or sometimes even more carbons without oxygen. Okay, the most important, and this is an extremely important molecule, the most important deoxy sugar is deoxyribose. So deoxyribose, this is the carbohydrate residue in DNA. Deoxyribose structure is this. Okay, so I didn't draw it as a zigzag, but it doesn't matter. I'm just drawing a bond line structure. And you see it's a 1, 2, 3, 4, 5. It's a pentose. It's an aldehyde. It's an aldopentose. But this carbon right here doesn't have any oxygen on it. So this is an example of, so this is deoxyribose. And it's an example of a deoxy sugar. Extremely important. And then we could also have dideoxy or trideoxy sugars, in which more than one carbon is missing oxygen. Okay, so this is another important vocabulary word that we see all the time in biochemistry. Deoxyribose, deoxy sugars. Normally, all of the carbons are bonded to oxygen in some way, but in some sugars, the carbon doesn't have any oxygen. Okay, so that's another little vocabulary word for you to internalize. Okay, now let's get into something really hard. And that is the carbohydrates are divvied up into two stereochemical families, the D sugars and the L sugars. So we have the D and L stereochemical families. Okay, so some sugars are D sugars, some sugars are L sugars. Okay, and so how we distinguish them, and this is kind of complicated, and this is also going to call back to mind all of that R and S stuff that we talked about earlier. Okay, so here would be the steps to determine whether it's a D sugar or an L sugar. Step number 1 is give the carbonyl group, give the carbonyl carbon the lowest possible number but begin numbering at the end of the chain. Okay, so you're looking for a the ketone or the aldehyde functionality, and you're numbering all of the carbons in the carbohydrate, but you're giving the carbonyl carbon the lowest possible number, but you have to start numbering at the end of the chain. Let me go through all of these rules, and then we can work some examples. Okay, step number 2, find the highest numbered chirality center. Okay, step number 3, and the last step here for right now anyway. Step number 3, if that highest numbered chirality center has the R absolute configuration, then that sugar belongs to the D family. If that highest numbered chirality center has the S absolute configuration, then that sugar belongs to the L family. So this D and this L, these are stereochemical descriptors, just like cis and trans and R and S and E and Z. So we always find this D and this L the very beginning of the name. And so they just are referring to what is the chirality of the highest numbered chirality center. Let's do some examples. All right, so anytime we're talking about carbohydrates, there's a whole lot of writing because the carbohydrate can have many, many carbons, and there will be a lot of OH groups on there. And now we're talking about stereochemistry, so we're going to have to dash and wedge everything. So just bear with me. There's all kinds of, a lot of writing involved here. Okay, first of all, is that a carbohydrate? It is. It's a polyhydroxyaldehyde. Okay, and so now we want to see, does this belong to the R, to the D or L stereochemical family? Okay, so step 1, I found the carbonyl carbon. Now I'm going to number all of the carbons in the carbohydrate, but I'm going to give the carbonyl carbon the lowest possible number starting from the end of the chain. So there's carbon 1, there's carbon 2, there's carbon 3. Okay, so I did step 1. Now step 2, the highest numbered chirality center. Well, carbon 3 is the highest number, but that's not a chirality center. Carbon 2 is the highest numbered chirality center. Okay, now I have to figure out, is it R or is it S there? So you tell me, is that R or is it S? So just take a minute to try to figure that out. So what is it? Is it R or S? I think it's going to be S, right? Because we have a hydrogen here, and that hydrogen lives on a dash. It's in the back. That's exactly where we need it to determine R and S. So this guy has, it's going to be OH 1, 2, 3. That's a counterclockwise sweep. So the highest numbered chirality center is S. That means that this belongs to the L stereochemical family. And this sugar would be, it's called L-glyceraldehyde. Okay, but that's not important. Oh, and you know another skill that we worked on earlier in the semester, not just determining whether it's R or S from a dash and wedge drawing, but we also looked at the skill of determining the chirality from a Fisher projection. Remember those where the east-west bonds are reaching out to hug you? Yeah, so let's try one of those problems. what about something like this? Bring him down. Okay, is that a carbohydrate? Oh, it most certainly is, because it's a polyhydroxy ketone. And it also has 1, 2, 3, 4, 5 carbons. So this is a ketopentose. But the question is, does it belong to the D or the L stereochemical family? So here I've drawn the structure not as a zigzag with dashing and wedging, but now as a Fisher projection. So this is another skill that we have to work on about whether the being able to determine the absolute configuration from a Fisher projection. Okay, so you try that, see what you come up with. Is this a D sugar or is it an L sugar? You're giving the carbonyl carbon the lowest possible number, but you have to start numbering from the end of the chain. And then find the highest numbered chirality center and determine whether that is R or S. Okay, the numbering. See, if I start here, if I'm calling this carbon carbon 1, the carbonyl will come in at 1, 2, 3, 4. That's no good. If I start numbering up here, the carbonyl is going to come in at 2. So there's carbon 1, there's carbon 2, there's carbon 3, there's carbon 4, there's carbon 5. That's the correct numbering. I'm numbering starting at the end of the chain of carbon atoms, and I'm numbering in such a way that the carbonyl group gets the lowest possible number. Right, so sometimes you start at the top and work down. Sometimes you start at the bottom and work up. Sometimes you start at on the right and go to the left, and sometimes in the reverse direction. You're just trying to give the carbonyl carbon the lowest possible number. Okay, so that's step 1. Now step 2, the highest numbered chirality center. Is carbon 1 a chirality center? No. Is carbon 2 a chirality center? No. How about carbon 3? No. How about carbon 4? Yes. How about carbon 5? No. So carbon 4 is the highest numbered chirality center. So whether this is a D sugar or an L sugar depends on what is going on here. And remember, in a Fisher projection, the east-west bonds are reaching out to hug you, and the north-south bonds are pointing away from you. So take a little bit of time. This is going to be a review of stuff we've covered before. Tell me, is this a D sugar or an L sugar? Okay, so over here, just to try to explain this a little bit better, I'm just going to focus on this chirality center here. So I have my chirality center there. I have OH. I have this oxygen, that's going to come in as group 1. That's going to come in as group 1. This hydrogen, he's going to come in as group 4, right? I'm doing the ranking, all right? And so now I'm at here, I go to carbon 3, I go to carbon 5. They're both carbons. I have a tie. What do? I have to go to the next set of atoms to break the tie. This guy's next set of atoms is what? OHH, right? I'm in the tiebreaker phase. Okay, this guy's next set of atoms is what? CHH. So I've written the next set of atoms in order of atomic number, high to low. And now the winner is the one that has the highest atomic number at the first point of difference. It's this guy. He wins. So this is rank 2, and this is rank 3. Okay, and so now this, remember in the Fisher projection, the east-west bonds are reaching out to hug you. So I'm standing here, and I'm looking at that hydrogen, and I see 1 is over here somewhere, 2 is down here, 3 is in the back. That's a clockwise sweep, but I'm looking at the molecule backwards. I'm looking at the molecule with the group of lowest ranking facing me. I reverse it for the right answer. This is an S absolute configuration, and this thing is an L sugar. Right, so that's just a review of the those figuring out the R and the S from different different representations. Okay, more about D and L. All right, so I'm going to try something here on my little console. If I can remember how to do it. Okay, so I hope that this worked. I hope you can see my little slides here. All right, so yeah, I just want to show you. We can see them. Oh, you can? Great, yes. Thank you. Okay, so why do we care about sugars in the first place? Well, if you're interested in biochemistry, if you're interested in dietetics or nutrition, you probably wouldn't be interested in any of that stuff if you didn't know that carbohydrates, sugar, is where we get a lot of our energy. So what I'm showing here on my slide is D-glucose, right? This is the only sugar from which you can get metabolic energy. It's a 1, 2, 3, 4, 5, 6. It's an aldohexose. It also belongs to the D stereochemical family because the highest numbered chirality center has the R absolute configuration. There's also L-glucose, but L-glucose is not a source of metabolic energy. Only the D-glucose can be used to derive energy. So that's why that's why these D and L designations are important. Okay, so you take glucose, you combust it enzymatically with oxygen, you get carbon dioxide and water, and in the process you liberate about 3,000 kilojoules per mole. Now, when you're interested in dietetics and in nutrition and in you probably aren't using kilojoules per mole. You're using calories, dietary calories per gram. And so maybe you know that a sugar provides about 4 dietary calories per gram. Where does that number come from? Well, when you take glucose and react it with oxygen and turn it into carbon dioxide and water, this is what's going on inside your body, that liberates about 4 dietary calories per gram. So that's where we get our metabolic energy from. Like this lady here on the treadmill, she's burning calories, right? Okay, we talked about the aldose and the hex, the aldose and the ketose. So there's glucose, there's our most important sugar. This is the sugar that is found in blood. If you're a diabetic, this is the sugar that you're testing for. D-glucose, it's an aldose, it's an aldohexose, and this is D-erythrulose. It belongs to the D stereochemical family. That's the highest numbered chirality center, must have the R absolute configuration. And let's see, is this going to work if I do that? Yeah. Where do we find Where do we find D-erythrulose? Well, it's not really important in food, but what it is important for is sunless tanning. D-erythrulose and dihydroxyacetone. Both of these are found in sunless tanning preparations. Have you guys ever heard of the Maillard reaction? Maybe if you don't cook, maybe you've never heard of it, the Maillard reaction. What is that? That is what happens when sugar gets together with protein and heat, and the protein and the sugar bond together, and the color of most of those compounds is brown. So imagine you have a hamburger, right? You put a hamburger on the grill. It goes from being red to brown, and brown food tastes good, right? That's the Maillard reaction. It's a sugar reacting with the protein and the meat to make something that's brown. And that's exactly how sunless tanning works. The sunless tanning ointment has sugar in it, D-erythrulose or dihydroxyacetone in it. Your skin is made out of protein, and just your body heat is enough to cause that Maillard reaction, and pretty soon your skin becomes brown or darker in color. Okay, we talked about deoxy sugars. There's 2-deoxyribose. This is the carbohydrate residue in DNA where carbon 2 doesn't have any oxygen in it. But 2-deoxyribose is not the only deoxy sugar. This is L5-deoxyribulose. It's a ketopentose. Every carbon has oxygen in it except for carbon 5. And that's deoxygenated, so that is why it's called 5-deoxyribulose. And it belongs to the L stereochemical family because because the highest numbered chirality center has the S absolute configuration. Okay, D sugar and L sugar, we talked about that. Here's another big important sugar for dietitians, D-fructose. This is fruit sugar. This is the sugar that's found in fruit. It belongs to the D stereochemical family, and a lot of these naturally occurring sugars, not all of them, but a lot of the naturally occurring sugars belong to the D stereochemical family. There is no L-fructose in fruit. All of the sugar in fruit is all D-fructose. There is no L-fructose in a piece of fruit. And this is one of the great mysteries of biochemistry. Why has Mother Nature selected the D stereochemical family as the linchpin of metabolism? Mother Nature did not choose the L stereochemical family, but only the D stereochemical family. Big unsolved mystery in biochemistry. But does that mean there are no naturally occurring L sugars? Oh, there are plenty of naturally occurring L sugars. L-rhamnose and L-fucose are examples, so there's some examples. And L-rhamnose, this is a carbohydrate that we find in poison sumac and also in poison ivy. So see that L-rhamnose is a 1, 2, 3, 4, 5. It's an aldohexose. I also see that carbon 6 here is deoxygenated, so it's a deoxy sugar. And furthermore, the highest numbered chirality center has the S absolute configuration. So that's what brings this into the L stereochemical family. So there are lots of L sugars, but metabolism is centered around the D sugars. That's the important one for dietetics, biochemistry, and so on. Sugar, it's not just for dinner, right? Sugars are messenger molecules. So you know about the blood types. Maybe we talked about this earlier in the semester. You know about the blood types. The various blood types result from the presence of carbohydrate residues on the surface of the blood cell. So this is supposed to be the blood cell. This is an acetal. It has a carbon bonded to 2 oxygens, neither of which is an OH oxygen. This is a carbohydrate residue. Here's another acetal down here. This is another carbohydrate residue. I believe that this is what the type O. I think this is the 2 sugars that determine what a type O is. So a carbohydrate, it's not just something that you eat. Carbohydrates are messengers. They're chemical messengers. This is how a blood cell communicates with another blood cell. Or this is how a blood cell communicates with an antibody. This is how a virus communicates with a blood cell, because the surface of the blood cell has all of these carbohydrate residues on it, and the virus and the antibody and the other cells are looking for that shape. Okay, yeah, here's a person undergoing some kind of transfusion or a blood draw. Oh, I feel for you, mama. I don't like that either. Okay, so let's see, stop. Let's go back to this. Okay, and now what do I want? I want speaker view. Oh, that was wrong. Oh yeah, speaker view. And I want speaker view. I want to get rid of all of these names up here. How do I do that? What's this about? No. Okay. Well, I don't know how to get rid of all of these names up here. So I'll just have to deal with it. Ah, okay. Miracle that I figured that out. Okay. So now let's continue. Let's get a little bit into the chemistry of the carbohydrates now that we had an introduction about how to refer to carbohydrates, and just had a little bit about where we find carbohydrates and a little bit about why they are important. In aqueous solution, carbohydrates exist as cyclic hemiacetals. So in other words, if you take a sugar, if you take a carbohydrate solid and dissolve it in a glass of water, or maybe in a beaker in a laboratory, that carbohydrate is going to, if possible, ring up into a 5-membered ring or a 6-membered ring, cyclic hemiacetal. But that's not just what a sugar does in a glass of water or in a beaker in a laboratory, because you're 85% water. You're nothing but a big bag of water with a bunch of chemicals dissolved up in there. And so the carbohydrates that are coursing through your blood right now, the carbohydrates that are being metabolized to give you energy, they are living inside your cell, and your cell is about 85% water. So the carbohydrate exists as a cyclic hemiacetal, either 5-membered ring or 6-membered ring, in a physiological system. So many, not all of them, but many carbohydrates exist as 5 or 6 membered ring cyclic hemiacetals in aqueous solution. And as I just said, this aqueous solution can be either a glass of water or a beaker in the laboratory or in the interior of your cell. So this is chemistry that we're already familiar with because we know what a hemiacetal is and we know how a hemiacetal forms. The recipe for the formation of a hemiacetal is an aldehyde or ketone and an OH group. And that OH group is coming from an alcohol, but as we saw at the last lecture, that we have a diversity of hemiacetal formation. So we can have an aldehyde or a ketone and a separate alcohol as 2 separate molecules, and they can react to form a hemiacetal, or we can start with a molecule that has an aldehyde or ketone somewhere in the molecule, and in the same molecule, 5 or 6 atoms away, we have an OH group, and that will form a cyclic hemiacetal. So this all fits in pretty nicely with the chemistry of the carbohydrates, fits in pretty nicely with what we're talking about before. Okay, so let's look at some situations. So here's a carbohydrate, and now I'm going to put an OH group 5 atoms away. 1, 2, 3, 4, 5. Is that a carbohydrate? No, because it's not polyhydroxy. So now I'm going to put, maybe I can put an OH group there. And just to make things fun, I'm going to make this a deoxy sugar, right? So that's a carbohydrate. And I see that the recipe for the hemiacetal is there. I see an OH group. I see an aldehyde or a ketone, in this case an aldehyde, under acidic or basic conditions, right? Acid or base. Under acidic or basic conditions, this thing is going to ring up into a 5-membered ring cyclic hemiacetal. So the product here is going to be this oxygen here is going to attack the carbonyl carbon. It's going to make a hemiacetal. What's a hemiacetal? Hemiacetal has a carbon atom bonded to 2 oxygens, one of which is an OH oxygen and the other one is not. So I'm going to ring this guy up to make a cyclic hemiacetal. This oxygen in boldface, that's him. And so oxygen, carbon, deoxycarbon here. There's an OH group over there. And this is now my hemiacetal. That's my hemiacetal carbon. And so this is what happens in aqueous solution, in that beaker, in that glass, or inside a cell. A 5-membered ring, cyclic hemiacetal. This is called a furanose. So there's more sugar vocabulary for you. It's easy to memorize this because this is a 5-membered ring. 5 begins with an F. The 5-membered ring cyclic hemiacetal is called a furanose. Okay, but we can also form a 6-ring cyclic hemiacetal. Okay, so let's look at a concrete example of that. How about this time, instead of an aldose, let's work with a ketose because this is going to be a little bit more complicated. And now I'm going to put an OH group 6 atoms away. 1, 2, 3, 4, 5, 6. Okay, and I could have swung this OH group down, but I didn't. I'm just trying to make this a little bit easier to understand. 1, 2, 3, 4, 5, 6. Yeah? Okay, is this a carbohydrate? It is. It's a polyhydroxy ketone, but it's kind of unrealistic because it's so highly deoxygenated. When we actually look at a structure of a carbohydrate, we're going to see OH groups everywhere, or lots of it, lots of OH groups. So I'm going to put an OH group there, and maybe I'll put an OH group there, and maybe I'll put an OH group there, something like that. Lots and lots of OH groups. Okay, so this is a under acidic conditions or under basic conditions, right? Inside a glass of water or inside a beaker in the laboratory, inside your cell, this thing can ring up into a 5-membered ring, cyclic hemiacetal. Okay, so that's the carbon that is going to be attacked. 6. So the attacking carbon here, I'm going to put him in boldface. He's going to be here. He formed a 6-membered ring. He attacked the dot. Okay, so now let's decorate the rest of the molecule. Boldface oxygen, CH2, and then we have a carbon atom that had OH on it. And then we had another carbon atom that had OH on it. And then we had another carbon atom that had OH on it. And finally, and at last, I've arrived at my dot. This is a hemiacetal. What's that? It has a carbon atom bonded to 2 oxygens, one of which is an OH oxygen. But we're not through yet because we still have this hydroxymethyl group to take care of. He's also bonded to the dot, so he's there. Okay, so that would be the 6-membered ring hemiacetal that this carbohydrate would form in aqueous solution. And these 6-membered ring cyclic hemiacetals, they're called pyranos. A pyranos. Okay, so that's more carbohydrate vocabulary here. Pyranoses and furanoses. And now there's a little bit more vocabulary to deal with because now we have to get back into the stereochemistry of the formation of these cyclic hemiacetals. Furanoses and pyranoses can be either alpha or beta. So this is another label that we can stick on carbohydrates, is that the furanose can be an alpha furanose or a beta furanose. Okay, so now let's go through the step-by-step and the rules here. If the hemiacetal carbon and the highest number chirality center have the same absolute configuration in other words, they're both S or they're both R, then this is called beta. Okay, and so what's an easy way to remember this? Well, what I do is same has 4 letters in it, S-A-M-E. Beta also has 4 letters in it, B-E-T-A. So that's just the cheesy way that I remember which one is alpha and which one is beta. If different, then the cyclic hemiacetal is called alpha. Okay, so those are the rules. So let's work some, as time permits, let's work some examples. First of all, the numbering. Begin numbering at the hemiacetal carbon. And remember, you're numbering carbon atoms. You're not numbering anything else. You're numbering carbon atoms. So before we do a concrete example, let's just look at the correct and incorrect number. Okay, so that's the hemiacetal. That's the hemiacetal that deoxyribose forms. And so we want to figure out, are we looking at the alpha or the beta hemiacetal? Are we looking at the alpha furanose or the beta furanose? This is the form that deoxyribose adopts in DNA. So this is very, very important. It's a big one, biggie for biochem. We begin numbering at the hemiacetal carbon. So that's carbon 1. But when we are numbering, we are only numbering carbon atoms in the chain. So we don't go 1, 2, 3. That's not a carbon atom. This is carbon 2. This is carbon 3. This is carbon 4, and this is carbon 5. So did you get that? Is that we begin numbering, carbon 1 is the hemiacetal carbon, and we're numbering only carbon atoms, and so this is the correct number. Okay, now what we need to do is we need to compare the absolute configuration of the hemiacetal carbon and the highest numbered chirality center. So there's the hemiacetal carbon. Is that a chirality center? No. Is that a chirality center? Yes, but it's not the highest numbered chirality center. This is. So our task now is to figure out what is the absolute configuration here and what is the absolute configuration there. Carbon 5 is not a chirality center. What's the absolute configuration at 1 and what's the absolute configuration at 4? And if they're the same, we've drawn the beta. And if they're not the same, we've drawn the alpha. So let's do that. So there's carbon 1, there's a hydrogen there. There's carbon 4, there's the highest numbered chirality center. So why don't you figure out, is this the alpha or the beta? What is the absolute configuration at carbon 1? One, 2, 3, hydrogen in the back. This is R. What's the absolute configuration at carbon 4? 1, 2, 3, hydrogen in the back. This is also R. So what I've drawn here, and the carbohydrate residue in DNA, this is the beta pyranose. are furanose. It's the beta furanose. Okay, and so now let's look at this guy over here. Okay, so all I've done is I switched up the pattern of dashing and wedging at carbon 1. So this guy is now the S absolute configuration. This guy is the R absolute configuration. The absolute configuration at the highest numbered chirality center and at the hemiacetal carbon are different. This is the alpha furanose. And how are the alpha furanose and the beta furanose related? These guys are diastereomers. And remember, diastereomers have totally different properties. And one of the great unsolved mysteries of biochemistry is why has Mother Nature chosen the beta furanose for DNA and never the alpha furanose? That's one of the great unsolved mysteries. Okay, well, our time now has expired. So as I leave you now, I have a little bit more to talk about carbohydrates. I have to slop over into Monday. But please check out the course website and read that blurb about the exam, the study guide. And if you have any questions about it, you can email me. Okay, so I must rush off to my next class, so I'll see you down the road. Until then.